Hello everyone, so thank you very much for the introduction and for the invitation. I'm very happy to be here to present some work from my group about egocentric multitask multimodal pre-training. So we studied human-centric computer vision in my group, and we study tasks like human pose estimation, human motion estimation, human scene interaction, hand pose estimation, or even, for example, to reconstruct closed avatars from images, from videos. So there are lots of tasks we can do, and they are all very challenging. But if we really want to understand human behaviors, I think we need to kind of zoom out a bit to see the big picture. I think the big picture about understanding human behavior here is humans are inherently multimodal. So both in how we express ourselves and in how we perceive the world. So for example, in terms of how we express ourselves, so we have body pose, we have facial expression, we also have speech, audios, and gaits. So gaits tells a lot about our attention, right? And in terms, so I consider this as inside-out information in terms of how we want to express our behaviors, right? And in terms of how we perceive the world, we can consider as the other way around, so outside-in information. So this information is also inherently multimodal, so including egocentric vision, so how we see the world, hearing, we hear a lot of sound, touch, even proprioception, right? So I think in order to really understand or model human behaviors to enable downstream tasks, for example, human-robot interaction, to design intelligent embodied devices, we really need to have a model that can capture, can model, and can predict human behavior from multimodality input. Okay. And there has been quite some work on egocentric multimodal modeling. I just list a few here, 3 here. So I think there is a kind of a common thread. One is on action understanding or visual question answering, right? So it's an important task for egocentric videos, and it also involves languages. So it's naturally like a very interesting multimodality model to study. And recently, there are also kind of people consider other type of modalities, for example, human motion, 3D human motion, and maybe MUs, maybe audios. So for example, this EgoLife data set I think is very interesting. It also includes other type of modality. But I think current exploration is still kind of limited in exploring the full spectrum of human-centric multimodal information. So for example, in terms of our perception, right? Just think about like a visual input. We are not just looking at the RGB videos, we also look at depth information, for example, object in the videos, normal maps, trackings, right? And in terms of the human-centric information, right, outside, so for example, human gaze or pose, right? So those are all kind of human-centric multimodality information. It's kind of not really integrated together. So towards this goal, we have been working on 2 projects. So the first one is egocentric multimodal data scaling up. So we presented egocentric synthetic data generator last year at CVPR 24. So I will first talk about this work. And then the second one I want to talk about is a follow-up work on that, where we start to explore how to do large-scale egocentric pre-training. So it's egocentric multimodal multitask pre-training, which we just put on archive. Okay. So let me start with EgoGen, an egocentric synthetic data generator. So I think this work, the way we see that is there are more and more egocentric data sets captured with different devices, with different modalities, right? With MUs, with all kinds of gates, with all kinds of different sensors. But if you think about like just the video input from the egocentric data, right? It's actually very hard to get ground truth information, for example, for depths, for normal maps, for segmentations. It's very hard because this egocentric, as we all know, it has a kind of significant domain gap between the data, egocentric data, and third view data. So we are lack of kind of efficient and scalable pseudo-labelers for that. So I think to get certain type of pixel level ground truth for egocentric video is very challenging. So that is basically the motivation of this work. So we want to create a synthetic data generator where we can generate all kinds of egocentric ground truth data for like pixel level ground truth data. Yeah, I don't know this kind of, yeah, okay. And if you think about this egocentric synthetic data generator, right? So we have lots of synthetic environment. We have, for example, different graphics assets. Or we also have virtual humans for body models, for example, simple. But what is the really key challenge for synthesizing egocentric data is we have to have realistic human behavior models, right? So because we are going to put the cameras on virtual humans, and then we are trying to generate synthetic data for the cameras that will be put on real humans. So we really need virtual human behaviors to be as close as possible to the real world human behaviors. So I think that's the key challenge for generating realistic synthetic data for embodied devices, especially cameras. So in order to do that, the student work on this whole pipeline, which is called EgoGen. So first of all, we use simple body models, right? It's widely used. And based on this body model, we can try to synthesize or try to generate data for different type of sensors, right? For example, for RGB cameras, depth cameras, or other type of sensors. And we also develop automatic closing simulation pipeline to put close on the simple body. So it's not technical novel here. It's just some speed up on the existing work so that we can have realistic human close when human move in the environment. And we also use some high quality things, but this can be replaced by application specific scenarios, right? And the key technical challenge here is the motion synthesis part, right? And here we propose this egocentric perception-driven motion synthesis model. So human motion synthesis itself is a topic people have studied a lot, so there is a community on that. And we consider, like, if we want to generate realistic human behaviors for egocentric cameras, right? We think like to really incorporate this egocentric perception component into this behavior synthesis is important. So that is a new component for this work. So basically, this motion model is kind of egocentric or ego-sensing driven. So instead of create, for example, an environment map or other type of features or encodings to encode the scene, so the virtual human here really try to perceive the environment from their own eye, right? So in the beginning, we tried to do this with depth image, but apparently it wasn't really fast enough to train the RL algorithm in the end. So we actually use a very compact last year used a very compact egocentric sensing feature to represent what people see from the environment. So the idea is the people's movement, like all this virtual humans movement, should really depend on what they see. And after they move, what they see changes, right? So there is a perception action loop even for this virtual human. So overall, this model is a MDP formulation. So we have state. So the state is basically include our body representation, which is a marker-based body representation. So I'm not going into the details. So basically, we represent human body with a set of about 60 markers. 3D locations to represent this human's location and motion, right? And we also have this egocentric perception feature to represent the environment. We also have the distance to the goal. So the behavior here we try to synthesize is very simple. So the virtual human has a target. So the virtual human basically trying to reach the target in an environment. So this is normally a 3D scene kind of environment, crowded. It could be also other humans. And then the virtual human has to observe the 3D environment, and then by observing the 3D environment, try to generate like the next motion, plausible motion to reach this target. So it's a simple behavior. Anyway, so this target is also a part of the state. Where the target is, how far it is from the virtual human. And we have a model. So this model is here. It's a generative motion primitive model. So what it is, essentially, it's a variational autoencoder, very simple model, and a conditional variation autoencoder. The input is my body, like my current pose, right, and like current 2 frames. And then these generative motion primitive models basically try to predict my next, like a half second, where should I move in order to achieve my goal, right? So this is a motion primitive model. It's generative, so we can generate different human behaviors because this model is generative. And we have an action. So in this MDP formulation, the action is basically the latent variables of our generative motion primitive models. It's not the traditional action type of action, it's a latent variable. And we also have a policy. So basically, it's a neural network that maps from state to action. So it's a neural network. It takes where am I, where is my target, what I'm looking at, what is my egocentric sensing, and then it's try to generate this latent variable to drive my body to go towards the goal, right? Meanwhile, try to avoid other object or moving object, static object in the environment. So this is a key idea of this motion synthesis model. And I want to show you 2 results. I mean, for people who study motion synthesis, it was very encouraging for us because, for example, our previous work, which is called demos, which use certain type of like environment features to encode the environment, it had a very hard time to do certain type of exploration. So to go beyond the training distribution to explore, okay, if there is a big wall, how do I really reach my target, right? But with this egocentric sensing, right, so we were able, or the algorithm was able to explore the policy such that the virtual human can actually find the way to reach the target. So this is very interesting for us at that time. Another one is very interesting is the motion diversity. So if you look at this, right, this was our previous work. So they try to synthesize like crowd behaviors in the sense each virtual human try to reach the target, like the opposite location in the circle, right? And you can see we don't really observe much motion diversity here. And in this work, and one thing is when we train our policy, when we train our model, we basically have a simulator. We randomly select or put like object in the environment. So we don't have a moving like environment. But somehow this policy was able to generalize to this such dynamic environment, right? So each virtual human actually moves, and we never trained in such way environment when for our motion model. And you can see each virtual human was trying to reach the opposite location, their target, with different type of motion, right? Someone walks very fast, for example, I don't know, this one? No, I don't remember. No one walks very fast. This one. And then someone walks slow, try to avoid other virtual humans, right? So, here. And you can see this is one policy actually generalized to different body shapes. Of course, we trained our virtual humans at different body shapes, but it works well, I think, in terms of the body shapes that are not too far away from the mean. Okay, so now we have this we have a way to basically put the virtual human in the 3D environment, and if we have a graphics assets, right, in the 3D environment, we can basically now render all kinds of egocentric data. And if we have the ground truth, we can also have the ground truth, right? For example, point tracks, depth maps, semantic segmentations, all kinds of ground truths. And okay, now we have this synthetic data generator. Let's see how we can use this for some egocentric tasks. So we showed 2 tasks. The first one is mapping and localization for AR. So we worked together with Microsoft on this task. So what Microsoft did is, together with ETH, is they create this Lamar data set. So they use HoloLens and I think also a pad to collect images from the ETH building, like someone wear HoloLens in the ETH building, and then they can create this structure from motion maps, right? But the problem is this map is kind of sparse, right? Because it's actually very hard to collect lots of data. You have to really have a student walk in the building. And now what we can do is, okay, they also have a laser scan of the building. Now what we can do is basically to put a virtual human, as many as we want, in this virtual building, and then now we can synthesize, or we can collect synthetic data from this virtual human's perspective, right? And since this virtual human's behavior is supposed to be close to the real human behavior, right? And then we hope this synthetic data, right, at least the camera angle, this type of distribution, maybe not the photorealistic yet, but the camera angle is close to the data that are captured from the HoloLens that are weared by real humans, right? So with this initial structure from motion map and together with this synthetic data, right, generated by EgoGen, now we can create a much more complete structure from motion map for the Lamar data set, and we test it on the test set. It actually gives better localization accuracy. Okay. So the second task we explored in our work is egocentric mesh recovery. So the task here is given egocentric image, right? For example, people talking to each other, one person wear an egocentric device. We want to basically estimate the 3D human body, ideally also motion from this egocentric view, right? And it's we collect a data set by ourselves 2 years ago, but it was very hard to collect. Like, we have very limited data set. And now with this EgoGen, we basically can create lots of synthetic data for this task, right? So basically we create 300K RGB and 105K depth training images of human moving in 3D environment. And so we don't have like a huge improvement on the RGB like estimation, but if the input is the depth, right, and the output is like a 3D human body, so that if that's the task, actually for example, the baseline pre-trained at that time was state of art. Pre-trained with our synthetic data actually improves the result by 20%. So it shows like this pre-training on this large scale synthetic data helps the estimation of human body from this egocentric view. Yeah. So what are the take-home messages here? I think one thing is like egocentric synthetic data generation. I think is another interesting application of generative human motion synthesis. So there are more and more people studying generative motion synthesis, and lots of people consider humanoid is a kind of application for this scenario, for this line of work, right? But I think egocentric synthetic data generation really needs realistic human behaviors. And this is a very interesting application for motion synthesis. And the second takeaway I want to share is egocentric perception-driven modeling is challenging. So that is what we try to explore, right? but it may be the key to scaling up the behavior synthesis, right? I think it's naturally we want to kind of create a loop between the egocentric perception and the behavior. And it's challenging, but that's probably the way we can really try to synthesize more and more realistic human behaviors, because we move because what we see, and we see because what we move, right? Okay, and the last one is, in this work, we have shown a very simple motion behaviors here. It's just a person trying to reach a goal in a 3D environment, potentially with other moving humans. But I think there are much more tasks to explore, right? Hand-object interaction, how to synthesize that realistically. Social interaction, how to synthesize that realistically. I think those are all open questions. Okay, so that's the first work. In the remaining 10 minutes, I want to explain, or I want to present our latest work, EgoM2P, so Egocentric Multimodal Multitask Pre-training. So as I mentioned, right, I think like a human behavior is inherently, humans are inherently multimodality. And I think egocentric data has a unique advantage here. We can really capture multimodal data with embodied devices, right? So here in this work, we basically explored 4 modalities, including egocentric RGB videos, depths, gates, and camera trajectories, right? There are many more modalities, but so far we explored these 4 for this pre-training model. And also the data amount is scaling up. So if we are talking about pre-training, right, one question is, do we have enough data for pre-training or foundational model, if you want to call it in that way? So I think we are getting more and more data, right? So we have EgoXO4D, right? So you folks here has collected lots of amazing data. So we have more and more real data. And we also have synthetic data. For example, our own EgoGen data, which actually quite complementary in terms of modality, in terms of capability compared to real data, right? Real data, we have very much like all kinds of semantics, behavior semantics, right? Humans do all kinds of things. We have sound, we have like a visual diversity, semantic diversities in the real world data, but it's very hard to get pixel level ground truth in the real world data. On the other hand, for the synthetic data, right, we can really have pixel level ground truth for many modalities, for depths, for normal maps, for tracks, right? But we don't have a rich semantic or behavior in the synthetic data, because we can only synthesize simple behavior so far. But these 2 things are quite complementary to each other. And both type of data are scaling up. So I think it's feasible to train a large-scale multimodal multitask egocentric vision models. So what are the challenges of doing that? So the first thing is really the heterogeneous modality annotations. So if you look at the data set, exists. So there are some data sets we have explored in our paper, in our project, and you can see they really have different types of modalities, and we are lack of effective pseudo-labelers. So maybe for depths we could have some pseudo-labelers, but for gates we definitely don't have really a good pseudo-labelers. And if you, for example, for bodies, if you never capture the bodies, the body is actually it's very hard to estimate, right? So we don't really have effective pseudo-labelers, and also the temporal consistency is hard to model compared to multitask image foundation models. And here I refer to the 4M model. If some of you work on the multitask image foundation models, for example, 4M models can basically incorporate 21 modalities. But for them, the way they train that is for each data point, right? They really have all this 21 modality, all the pseudo-labelers available, right? And it's not the case here. If I take a training example from, for example, HoloAssist, right? It has certain modality, but it certainly lacks certain other modalities. If I take EgoGen, right, I don't really have gates because we were not able to synthesize gates. Okay, and also another thing is for this foundational model, right, it's a fast changing camera pose is hard. So it's even for like, for example, video models, I think this fast camera changing is still sometimes you don't really see a good result. So that's a challenge also related to egocentric temporal foundational model. Okay, so so as I mentioned, right, we tried to have a pre-training model, and on the model side, so our principle is actually the first thing this model should be really simple, like should be modular, and should be really easy to train, like an easy training objective, because we want it to be scalable. So we have basically studied, for example, 4 modalities for now. So we designed gaze tokenizers. So we basically tokenize gaze. We have camera tokenizers to tokenize cameras. We also use Cosmos tokenizer to tokenize depths and RGB frames, right? So now we have this 4 type of modality, and in total we create a 4 billion multimodal token basis. And given this multimodal token database, we basically leveraged this very simple masked autoencoder framework, right? So for this framework, given all these tokens from different data sets, we basically first have a modality-specific embedding layers, and then we basically have a transformer masked autoencoder, like a transformer encoder and decoder, to basically try to do this, try to learn these features, right? Try to do this pre-training, and we train this model using 251 H100 GPUs and 16 hours, and we train this multitask, multimodality model. So now I want to show you like how this model performs, right? So the first thing we tested, I was very interested in the gates. Can it really predict gates, right? So if you think about it, it's kind of so how to say, like we have training data from all kinds. I don't know why the video is not playing, but I guess it's fine. So if you think about it, we have really data from all different egocentric data set, right? Some have gates, some doesn't have gates. Now the question is, when we train this modality to modality, this estimation, right? Can we really estimate the gates for the data set that actually didn't have gates before? Right, so that's a question we are trying to face. Can we have this transfer capability from data set to data set? Unfortunately, you don't really see, it's just my laptop. It seems you can see that. It's pretty good. Okay, sorry, it's my laptop. So you can see it actually performs better than our baselines. And then the second task we tried is egocentric camera tracking, right? So given the video sequence from RGB sequence, we tried different camera tracking algorithms, and ours performs quite well. And I also want to show you some numbers, and I want to draw your attention to this, right? So I think our method is not, so this is trained on lots of data, right? Okay, for this ADT data set, it was never included in the training, right? In the pre-training, but still it's kind of generalized to even outperform the baselines on the ADT method. And what is really interesting is now this very simple task to modality model can perform much more efficient than task-specific method. And also we tested on depth estimation, and you can see this is RGB input. We have ground truth depths, rolling depths, Alliance 3R, and hours. And this is on the ANSI dataset, HOI4D, which we never seen during the training. And you can see ours actually performs better than the baselines, and these are also the numbers. So you can see on both the scene data set, so on the test set, as well as on the unseen data set, like completely unseen, no, even not training, even not included the training data in our pre-training, you can see the depth estimation is also pretty reasonable. And the time, like the efficiency, inference time is much faster than the previous work. So the last thing I want to show you here is video synthesis. So this is kind of challenge for our model because when key challenge here is when we try to do the tokenization for all kinds of modalities, right? We have way more tokens for RGB and depths than the gates and camera. You can understand. So the camera is really just 6-degree of freedom, right? The gates, is also a very small amount of data, but the RGB and the depths are much more data, right? So we have this huge imbalance between the different tokens, and one thing we had to do is basically to to do downsampling both in temporal domain as well as in the spatial domain for the RGB and depths. So that's why actually it's a very hard task to do the RGB synthesis, because the token is really look at downsampled information. Nevertheless, so this is the input depth. And let's see, so if we tested a control video, yes, a control video, you can see the video synthesis is not really, the pixels is not really convincing. And we also tested control video, it's not also convincing. And at least our method produce certain kind of visual realism, but it's not completely realistic yet, or not completely useful yet, I think, for the video synthesis task. Okay, so what are the take-home message for this work? I think egocentric synthetic data can help data scaling. So in our paper, we show that EgoGen actually helps. And I also want to say Ego M2B, this pre-training remains scalable to the evolving data set and new heterogeneous modality. So I think now it's just a starting point. We include certain data set and certain modality, but there are more and more data sets, and we should really consider more and more modalities. And we have a framework which is modular, which is scalable. So I think we should be able to do this in an even larger scale, right? In both in terms of the modality as well as in terms of the data. And it also starts to show promising zero-shot capability. Okay, so these are the references. The work of the code of first work is online, and both work are led by my PhD student, Gen Li, who will be looking for an internship next year. So if you are interested in hiring an intern, you can reach out to him. He's great. Thank you very much.